In this video, we're going to talk about extrema on an interval. Chances are you've heard of extrema before in terms of a minimum or maximum of a function. And in this video, we're going to be talking about extrema on an interval. So we're going to restrict our x values to take a look at the maximum and minimum points within an interval for f of x. Personally, the easiest way that I identify mins and max or any kind of extrema is by graphing the function itself. It's pretty obvious when you look at a graph of something. So for example, if I take this graph here, this point 0, 1 is my minimum and this point 2, 5 is my maximum since it's its highest and lowest points. But the next two examples, there are holes in the function. So for example, in this one, these have two holes at their endpoints of that interval, and so this point up here may look like a maximum, but it's not because there's a hole there, so that point doesn't exist. And then here we have a removable discontinuity. That's not a minimum right there either because that is a discontinuous function. So that's where the extreme value theorem comes in. It says for any function, if it's continuous on a closed interval from whatever a to b is on the x-axis, then that means that that function has both a minimum and maximum on that given interval. So while a function can have absolute, or what we call global, max and min, that means that it is the highest or lowest point in the entire graph, or whatever our interval is. This slide talks about something called relative extrema. So that's relative max and relative min, or you might hear of it as local max or local min. That means that, for example, here in this graph, this is a local maximum and this is a local minimum, but you might notice that the graph will go down here towards negative infinity and up here towards positive infinity on the y-axis. So these 2 points, because I only have a snippet of this graph, are relative extrema because it's local to this certain cutout of the graph, and it may have max or min, absolute max or min elsewhere on the graph, but for now I know that these 2 points here are the local extrema. So let's take this example, and let's say I have this function here, f of x, which is defined in that blue box, and it appears as though I have a relative maximum at 3, 2. So I'm going to take the derivative and see how that will help me figure out if that actually is a relative max. So there are a couple different ways that you could take the derivative here. You could use the quotient rule. I decided to go with the product rule, so I simplified this part here, pulled out a 9, so it's just the constant multiple rule. And I rewrote this as this guy, so I took the derivative and I simplified it. There's a ton of different ways you could simplify it as well. But what I'm actually going to do here is plug in 3 and see what the slope of that tangent line at this relative max will end up being. So when I plug in x equals 3, I end up with a 0 in the numerator, so that means that the slope at that point of the tangent line is going to be 0, so it's a horizontal tangent line. Our next example here is the absolute value function, and looking at this graph I can tell that there is a relative minimum at the origin 0, 0, and if I was going to take the derivative of f of x equals the absolute value of x, I have to take it as the definition of the limit coming from the left and from the right, and they're going to have different limits. So coming from the left I get -1, coming from the right I get 1 at 0, x equals 0. So the derivative is not going to exist there. And next let's take the sine function. So I have 2 things here within this interval. I have a relative max at pi over 2, 1, and a relative min at 3 pi over 2, -1. So let's take the derivative of this and see what happens when I plug in pi over 2 and 3 pi over 2. So the derivative of sine is cosine, and when I plug in pi over 2 and 3 pi over 2, according to the unit circle, cosine of both of those values is 0. So much like what happened 2 examples ago when I plugged in an extremum point, I ended up with 0 as the slope of the tangent line. So those 3 examples lead us to the conversation in calculus about critical numbers. So that's when I have a function f, and if I take the derivative and I plug in some value c along the x-axis, and if I plug that in to the derivative and it equals 0, like we had in some examples, or the original function is not differentiable at that point, then c is a critical number of f. So for example, here's something where we have a point and it comes back down. This, I can't differentiate at that c point. So that's a critical number of the original function, much like the absolute value function we looked at. Also, if I get a horizontal tangent line where f prime of whatever that c value is equals 0, that's also a critical number. And that's going to help us out when determining maximum and minimum points on a graph. So here are the 4 major guidelines for finding extrema on a closed interval, especially if you are looking to do this algebraically, either with or without a graph to help you. So if you have a function on a closed interval from a to b, you're going to first find the critical numbers. So you're going to have to take the derivative and then set that equal to 0 to see if you can actually find the critical number there. And then you're going to evaluate f at each critical number in that interval. And then you must evaluate it at each endpoint because they could be extrema themselves. And then at least one of those values is the minimum and the greatest is the maximum. So let's do a couple examples to work these steps out. So my first function here is this f of x, so 3x to the 4th minus 4x to the 3rd, and I'm only looking on the interval where x is between -1 and 2 inclusive. So the first thing I'm going to do here algebraically is take the derivative of f of x. So here's our f prime of x, a pretty simple derivative to take. So I first want to check out the critical numbers. So that means that I'm going to have to set this equal to 0 and see if I can't find my x values that will produce critical numbers. So I set this thing equal to 0 and I'm able to factor out a 12x squared and an x minus 1 here. So that gives me x equals 0 and x equals 1. I plug in 0 and 1 into the original f of x, not the derivative, and I find these 2 points. So I have the origin 0, 0 and 1, -1. So even without this graph, I could tell that this could be a relative minimum. This might be a relative max, but let's plug in -1 and 2 into f of x and see if we get more information. So I am able to find 2 more points, -1, 7 and 2, 16. 2, 16 stands out as the maximum, and the minimum is still going to be 1, -1. So this graph confirms it here, but algebraically we can prove it here as well. So our next example takes this function f of x is equal to 2x minus 3x to the 2/3, so keep in mind that the x is the only thing, to the power of 2/3 on the interval from -1 to 3 inclusive. So first things first, I'm going to take the derivative of f of x and set it equal to 0, see what kind of critical numbers I'm working with. So once I start taking the derivative of f of x, I quickly realize that I am going to have an x in my denominator somewhere because I have a negative exponent hanging out. So there are a lot of different ways you can write this. This is just one of them. But I noticed that x can't be 0. So f prime at 0 does not exist. So that was one of our critical number pieces, is that although the critical number itself can exist and it could be a max or min point, but if the derivative at that critical point doesn't exist, it's also a critical number. So what I did with that 0 is I plugged it into the original f of x and I got out 0, 0, or the origin, which looks like it could be a maximum. So the other 2 numbers I now need to plug in to f of x is -1 and 3 and see what I get. So when I plug in these 2 numbers here into f of x, I get these 2 points, which are also on our graph, and even algebraically I can deduce that this point is going to be my minimum, and one of my critical points is 0, 0. So my max is the origin, and my min is -1, -5. And for our last example, let's find the extrema of f of x is equal to 2 sine x minus cosine 2x, and we're going to limit it to the interval of 0 to 2 pi inclusive. First things first, going to take the derivative of f of x and see if I can't find any critical points from that. So the first thing I do is take the derivative of f of x. So derivative of sine is cosine, derivative of cosine of 2x is going to require the chain rule here. So I end up with 2 cosine of x plus 2 sine of 2x. Sine of 2x can be replaced with 2 sine x cos x, which is lovely because I don't have any 2x's, I don't have any squares in here. I can actually pull out a 2 cos x and I'm left with 1 plus 2 sine x. And I'm going to set that equal to 0 to see if I can't find my critical numbers. And so I do that, I'm able to isolate 2 cos x equal to 0 and 1 plus 2 sine x equal to 0 and solve for cosine of x and sine of x. And using the unit circle, I find 4 values between 0 and 2 pi that satisfy this statement here. So that's pi over 2, 3 pi over 2 for cosine, and 7 pi over 6 and 11 pi over 6 for sine. And so my next step from there is to plug all 4 of those points into the original f of x. So I was able to do that, and I found one maximum, which is at pi over 2 comma 3, and 2 minimums because they reach the same low point on that interval at -3/2 on the y. So that's at 7 pi over 6 and 11 pi over 6. And that's going to do it for this video. Thanks for watching.